Welcome back to Signal 2030, where we explore the scientific breakthroughs shaping our future. This is part 4 of our series on nuclear fusion, where we take a step back from the core designs and dive into the engineering realities of fusion. From withstanding extreme heat and neutron bombardment to building systems that can operate continuously at scale, we'll look at the toughest challenges standing between fusion and the power grid. We'll also explore some of the alternative fusion concepts that could offer a different path forward, outside the traditional magnetic and laser-based approaches. Okay, so whether it's the patient magnetic approach or the explosive inertial one, achieving fusion isn't just about hitting that triple product. There seem to be these huge engineering hurdles that are almost universal. Let's talk about some of those. First up, taming the yeast, plasma stability and control.
Absolutely. Even if you achieve the basic conditions for fusion, the plasma itself is an extraordinarily complex and dynamic medium. It's inherently turbulent and prone to a whole host of instabilities that can degrade confinement, reduce performance, or even, as we discussed with tokamaks, catastrophically terminate the discharge. Keeping the plasma well-behaved is critical.
What kind of bad behavior are we talking about? You mentioned MHD instabilities for tokamaks.
Right. Magnetohydrodynamic MHD instabilities are generally large-scale fluid-like distortions of the plasma. They arise from the complex interplay between the plasma pressure gradients, the electrical currents flowing within it, and the confining magnetic fields. They represent a major threat to stable operation in magnetic confinement devices.
Yeah.
Besides the major disruptions, you can get things like kink and sausage instabilities, where the plasma column itself develops helical twists or gets pinched off in places, potentially bringing the hot core into contact with the reactor walls. There are also tearing modes. These happen when magnetic field lines, which should ideally form nice nested surfaces, break and reconnect in undesirable ways. This can form structures called magnetic islands within the plasma.
Magnetic islands, like little isolated regions?
Exactly. And these islands act as shortcuts, allowing heat and particles to rapidly leak out from the hotter core to the cooler edge, significantly degrading confinement. And then particularly in the H-mode operation at tokamaks, you have those edge-localized modes, or ELMs.
Right, the edge bursts.
Yes, these are quasi-periodic, violent bursts of particles and energy that erupt from the very edge of the plasma pedestal. While they help to control impurity buildup, they also deliver intense, transient heat loads to the plasma-facing components, especially the divertor, which can cause erosion and limit component lifetime. Controlling or suppressing ELMs without losing the good confinement of H-mode is a major challenge.
So even if the whole plasma doesn't collapse, you have these leaks and bursts chipping away at performance, and you mentioned turbulence too.
Yes, even when the plasma is macroscopically stable, no large kinks or tearing modes, it's often intrinsically turbulent at small scales. Think of it like swirling eddies in a fluid. These small-scale fluctuations in plasma density, temperature, and electric potential drive what we call anomalous transport.
Anomalous meaning unexpected.
Meaning much faster than predicted by simple, classical collision-based physics. This microscopic turbulence causes heat and particles to leak out of the plasma core much more rapidly than they otherwise would. In fact, this turbulent transport is often the primary energy loss channel in MCF devices and the main factor limiting the energy confinement time, PEAT. Understanding and controlling this turbulence is absolutely critical for achieving efficient fusion power.
It sounds like trying to hold smoke in a sieve sometimes.
Yeah.
Let's revisit those catastrophic disruptions in tokamak. You said they're really bad. Can you elaborate? Especially the runaway electrons part.
Sure. Disruptions are really the Achilles heel of the conventional tokamak concept, especially as you scale up to large, high-current devices like ITER or a power plant. As we said, it's a complete loss of plasma confinement in milliseconds. It typically happens in two phases. First, there's a thermal quench. The plasma rapidly loses its thermal energy, cooling down dramatically in maybe a millisecond or less.
Everything goes cold fast.
Very fast. This is followed by a current quench. As the plasma cools, its electrical resistance shoots up, causing the large plasma current, remember millions of amps, to decay rapidly, often in just tens of milliseconds. This rapid change in a huge current induces enormous electromagnetic forces, like the forces in an electric motor, but huge on the vacuum vessel, internal components, and magnet coils. These forces can be strong enough to physically break things if the structures aren't incredibly robust.
Okay, huge forces. What about the runaway electrons?
This is a particularly dangerous phenomenon that can occur during the current quench phase, especially in large machines. As the plasma disrupts and cools, the resistance drops initially, but the electric field that was driving the current is still there, induced by the changing magnetic fields. This large electric field can grab some of the electrons in the plasma and accelerate them to extremely high energies, relativistic energies, close to the speed of light.
Electrons moving near the speed of light inside the reactor.
Yes, these become runaway electrons. Because they're moving so fast, they barely interact with the rest of the plasma and are not well confined by the decaying magnetic fields. They can form a beam of highly energetic electrons, carrying potentially megaamperes of current. If this beam impacts the reactor wall,
Bad news.
very bad news. It can deposit its energy in a very small area in a very short time, causing localized melting, vaporization, and severe damage to the plasma-facing components. Preventing the formation of these runaway electron beams or finding ways to mitigate their energy before they hit the wall is one of the highest priority research areas for ensuring the safety and viability of large tokamaks. It's a potential showstopper if we can't manage it.
Yikes. Okay, so plasma is clearly a wild beast. How are scientists actually trying to tame it? You mentioned AI. That sounds futuristic.
It is futuristic, but it's happening now. Controlling these complex plasma behaviors in real time is incredibly challenging. You have hundreds, maybe thousands, of sensors measuring everything from temperature and density profiles to magnetic fluctuations and light emission, and you need to react in milliseconds using actuators like magnetic coils or gas puffs. This raises an important question. Can we get ahead of these instabilities? Can we predict them and steer the plasma away from dangerous territory?
And AI can help.
It seems so, yes. This is a particularly promising frontier, applying modern artificial intelligence and machine learning techniques to plasma control. For example, researchers at facilities like the DID National Fusion Facility in San Diego and also at JET have been developing AI algorithms.
What do these algorithms do?
They can monitor all those sensor signals in real time, learn the complex patterns that precede an instability like a disruption, and then dynamically adjust things like the currents in magnetic control coils to actively steer the plasma away from those disruptive conditions without actually triggering the disruption itself.
So real-time steering of a star in a bottle using AI.
That's essentially what it is. It's incredibly sophisticated feedback control, moving beyond pre-programmed responses to truly adaptive, intelligent control based on machine learning models trained on vast amounts of experimental data. It's a very exciting development that could be crucial for making tokamaks, in particular, more reliable.
Okay, that's some hope on the control front. Let's move to the next big universal challenge, the crucible. Managing the extreme heat and the interactions between the plasma and the materials. The plasma-material interface, or PMI?
Right. If controlling the plasma is challenge number one, dealing with the consequences of that plasma touching or nearly touching solid materials is arguably challenge number 1A. The interaction between a 100 million degree plasma and the reactor wall materials is, without exaggeration, one of the most daunting engineering challenges in all of fusion energy development.
How do you even manage that interface? You can't let the core touch the wall.
You manage it very carefully, and you use specialized components. To protect the main chamber wall from the bulk of the heat and particle exhaust, most modern magnetic confinement devices, especially tokamaks and stellarators, employ a component known as a divertor.
The divertor, you called it the heat exhaust pipe earlier.
That's a good way to think of it. The divertor uses a special magnetic configuration, extramagnetic coils, usually placed at the bottom, or sometimes top and bottom, of the vacuum vessel. These coils create a magnetic X-point, which effectively peels off the outer layer of the confined plasma. This outer layer is called the scrape-off layer, or SOL.
Okay.
The magnetic field lines in the SOL, instead of closing on themselves within the main plasma volume, are diverted or guided downwards or upwards into a separate chamber. There, they strike heavily armored target plates.
So you direct the exhaust to a specific reinforced area?
Exactly. The diverter serves three absolutely critical functions. First, heat exhaust. It handles the majority of the thermal power flowing out of the plasma, channeling it to the target plates where it can be removed by high-performance cooling systems. Second, ash removal. It's the primary exit route for that helium ash produced by the DT reactions, preventing it from building up and poisoning the core plasma. Third, impurity control. Impurities sputtered or eroded from the wall materials tend to get ionized in the SOL and swept into the diverter along with the fuel particles, minimizing their ability to penetrate back into the hot core plasma where they would radiate energy and cool it down.
So the diverter is like the kidney and the exhaust manifold of the reactor all in one.
A very good analogy. It's a critical multi-function component. But because it's intercepting all this heat and particle flux, the components within the diverter, what we call plasma-facing components, or PFCs, especially those target plates, face an absolutely hellish environment. unprecedented hostility, really.
How hostile are we talking?
Well, first, there's the high heat flux. Even in steady-state operation, the heat loads concentrated onto the diverter strike points can reach 10 to 20 megawatts per square meter.
10 to 20 million watts on a square meter. How much is that?
For comparison, the surface of the Sun is about 60 megawatts or more. The heat shield on the space shuttle during re-entry experienced maybe 1 to 2 megawatts.
So it's significantly higher than re-entry heat loads, sustained continuously. And that's just the steady state.
It gets worse.
Oh, yes. During transient events like those ELMs we discussed, or heaven forbid, a disruption, the heat loads can spike momentarily to several gigawatts per square meter, thousands of megawatts for milliseconds. That kind of power density is capable of instantly vaporizing literally any known solid material.
Vaporizing anything.
Wow. Okay, heat is bad. What else?
Then there's the intense particle bombardment. The diverter targets are continuously bombarded by a high flux of energetic ions, deuterium, tritium, helium ash, as well as neutral particles. This constant sandblasting causes physical sputtering.
Sputtering, like sandblasting atoms off. Energetic particles hitting the surface knock atoms loose from the material lattice. This erodes the material over time, limiting component lifetime, and the sputtered atoms can enter the plasma as impurities, which is bad for performance.
Okay, heat and particle bombardment, that's bad enough. But you also mentioned neutrons.
Ah, yes, the 14.1 MeV neutron damage.
This is perhaps the most insidious and long-term materials challenge, especially for DT fusion. Those high-energy neutrons, remember, are neutral, so they fly right through the plasma and penetrate deep into the surrounding structures, the first wall, the blanket, the vacuum vessel, everything.
And they damage the materials as they go.
Profoundly. Over the operational lifetime of a reactor, the cumulative effect of this intense neutron bombardment causes significant damage at the atomic level. The neutrons knock atoms out of their normal positions in the material's crystal lattice, creating defects like vacancies and interstitials. This is called atomic displacement damage. Even more uniquely for fusion neutrons, their high energy can induce nuclear reactions within the material itself, causing transmutation. Atoms of the structural material are literally converted into different elements. For example, tungsten atoms can be transmuted into rhenium or osmium. Hydrogen and helium gas atoms are also produced within the bulk material.
So the material itself changes its composition over time. Neutrons eating metal, as you put it.
That's a pretty accurate description of the effect. All this damage, the atomic displacements, the buildup of transmutation products like helium gas bubbles, leads to severe degradation of the material's properties. It causes embrittlement, making the material brittle and prone to fracture. It causes swelling, changing the component's dimensions. It reduces thermal conductivity, making it harder to cool. It basically severely limits the functional lifetime of any material placed near the plasma. Finding materials that can withstand this high-energy neutron fluence for years is arguably the single biggest material science challenge for realizing commercial fusion power.
So, given this hellish environment, extreme heat, sputtering, neutrons eating the metal, what materials can possibly stand up to it? It sounds like a real dilemma.
It is a huge dilemma, and engineers are constantly weighing the pros and cons of different candidate materials. For the diverter targets, the components facing the highest heat loads, tungsten, WA, is currently the leading candidate for next-step devices like ITER.
Why tungsten?
Its main advantages are its extremely high melting point over 3,400 degrees Celsius, the highest of any metal, good thermal conductivity to help remove heat, and relatively low sputtering yield compared to lighter metals,
which minimizes erosion and plasma contamination since it doesn't contribute much impurity due to its high atomic number, or high Z.
Sounds good. What are the drawbacks?
Tungsten's main drawbacks are its inherent brittleness, especially at temperatures below about 600 degrees Celsius, which can occur during startup or shutdown, and the fact that it becomes even more brittle under neutron irradiation. So there's a risk of cracking and failure.
Okay, so tungsten for the hottest parts, but it's brittle. What about the main wall, the larger surface area facing the plasma?
For the main wall, where heat loads are generally lower, but sputtering is still a concern, beryllium has been used successfully, for instance in the J-Chi tokamak. Beryllium's main advantage is its very low atomic number, Z4. If beryllium impurities get into the plasma, they radiate much less energy than high Z impurities like tungsten, making the plasma more tolerant to contamination.
Low Z is good for plasma. Downsides?
Beryllium has a much lower melting point than tungsten, around 1,287 degrees C, so it can't handle the highest heat loads. It also tends to trap a significant amount of tritium fuel, which is an issue for fuel inventory and safety. And beryllium dust is toxic, which complicates handling and maintenance.
Okay. Any other contenders? I thought carbon was used sometimes.
Carbon fiber composites, CFCs, were indeed favored for a time, especially for high heat flux areas, because they have excellent thermal shock resistance. They don't crack easily under rapid temperature changes, and they sublimate rather than melt at very high temperatures. However, CFCs suffer from severe problems with chemical erosion, reacting with hydrogen isotopes in the plasma to form volatile hydrocarbons like methane. And most critically, they readily absorb and trap very large amounts of tritium within their structure.
Tracking tritium is a big no-no.
A huge issue for fuel economy and safety regulations. For these reasons, carbon materials have been largely abandoned for the plasma-facing components in future reactor designs like ITER and DEMO, although research continues on advanced composites.
It really highlights the interconnectedness, doesn't it? The plasma physics dictates the conditions, the materials have to survive those conditions, but the materials failing can then poison the plasma.
Exactly. You hit on a critical feedback loop. To achieve better plasma performance, physicists often need to push devices into operating regimes, like the H mode, which unfortunately tend to produce transient events like ELMs that really punish the materials. The subsequent damage and erosion of these materials can then release impurities back into the plasma, which cool it down, radiate energy, dilute the fuel, and degrade the overall plasma performance. Plasma physics and material science are locked in this kind of adversarial relationship, demanding constant co-optimization. You can't solve one without considering the other.
So how are researchers trying to break this cycle? Are there advanced material solutions on the horizon?
Yes, absolutely. This is a very active area of research. To overcome the limitations of conventional solid materials,
like pure tungsten.
researchers are exploring some really innovative solutions.
What are those?
One promising direction for tungsten is developing tungsten composites. For example, tungsten fiber reinforced tungsten. This basically involves embedding strong tungsten fibers within a tungsten matrix, much like steel rebar is used in concrete.
Rebar and tungsten. Why?
The idea is to use extrinsic toughening mechanisms. Even if the tungsten matrix material becomes brittle due to neutron damage and starts to crack, the strong fibers bridge the crack, preventing it from propagating catastrophically. It provides crack resilience and tolerance, making the material much tougher and more reliable even after irradiation.
That sounds clever. Anything even more radical?
Oh yes, a truly radical and potentially transformative concept involves replacing solid plasma-facing components altogether with continuously flowing liquid metal walls.
Liquid metal walls, like in Terminator?
A little less dramatic, maybe, but the same principle. The idea is to have surfaces, particularly in the divertor, made of a thin, flowing layer of liquid metal, such as pure lithium or a tin lithium eutectic alloy.
Flowing liquid metal facing the 100 million degree plasma. How does that help?
It offers several potentially game-changing advantages. First, a liquid surface is inherently self-healing. If it gets damaged by sputtering or intense heat loads, the flowing liquid just replenishes itself. Second, it's largely immune to the permanent degradation caused by neutron damage that plagues solid materials. The liquid structure doesn't embrittle or swell in the same way. Third, certain liquid metals, particularly lithium, can actively pump out hydrogen isotopes and impurities from the edge plasma, effectively cleaning the plasma and improving performance. And fourth, the flowing liquid can serve double duty as both the heat transfer fluid and potentially part of the tritium breeding system if lithium is used.
Self-healing, radiation-resistant, cleans the plasma, handles heat, and breathes fuel. That sounds almost too good to be true. What are the catches this time?
As always, there are significant challenges. Handling flowing liquid metals in a complex magnetic and nuclear environment is incredibly difficult. Magnetohydrodynamic, MHD, affects interactions between the flowing conductor, the liquid metal, and the strong magnetic fields can create forces that impede the flow or cause instabilities. Evaporation of the liquid metal at high temperatures could contaminate the core plasma. And just the basic engineering challenge of reliably containing and circulating these hot, often corrosive liquids in the intricate geometry of a fusion reactor is immense. But the potential benefits are so large that several research groups and private companies are actively pursuing liquid metal PFC concepts.
Okay, so we've covered the main magnetic approaches to tokamaks and stellarators and the main inertial approach, laser-driven ICF. But you mentioned there is a whole ecosystem of other ideas out there, the frontier explorers.
That's right. While tokamaks, stellarators, and large laser facilities represent the mainstream, heavily funded paths based on decades of research, there's also a vibrant and diverse ecosystem of alternative fusion concepts being explored, often by smaller research groups or venture capital-funded private companies.
What makes them alternative?
Generally, they seek to either combine perceived advantages from both magnetic and inertial confinement, or they try to exploit completely different plasma physics regimes, often with the goal of achieving fusion in a potentially more compact, simpler, or more efficient device compared to the mainstream approaches.
Okay, give us a couple of examples.
One interesting category is magnetized target fusion, MPF, which is sometimes also called magneto-inertial fusion, MIF. As the name suggests, this is truly a hybrid approach. It tries to operate in an intermediate parameter space somewhere between the low-density long confinement of MCF and the ultra-high density short confinement of ICF.
A mix of both. How does that work?
The typical principle involves two main steps. First, you create a warm, moderately dense, magnetized plasma target. This target isn't hot enough or confined long enough for ignition on its own. It might be something like a field-reversed configuration, FRC, or a spheromac, which are types of self-contained plasma structures.
Okay, a warm magnetized blob of plasma. Then what?
Second, you rapidly compress this magnetized plasma target using some kind of imploding pusher, often a cylindrical or spherical solid or liquid metal shell called a liner. The crucial idea here is that the magnetic field embedded within the initial plasma target acts as thermal insulation during the compression. It significantly reduces energy loss from the plasma core, allowing fusion conditions to be reached with much slower implosion velocities and lower driver energies than required for traditional unmagnetized ICF.
So the magnet helps hold the heat in while you squeeze it.
Exactly. MTF aims to combine the reduced thermal conduction losses you get from magnetic confinement with the efficient plasma heating you get from mechanical compression. This could potentially lead to more compact and efficient fusion systems, perhaps relaxing the extreme requirements on the lasers or other drivers needed for pure ICF.
Sounds promising. Challenges?
Still immense, of course. Maintaining the stability of that initial magnetized plasma target during the violent compression phase is very difficult. Preventing the liner material itself from mixing turbulently with the hot fuel plasma, which would quench the reaction, is another major issue. And similar to ICF targets, for a power plant using disposable solid liners, you have that COPEC problem. They need to be incredibly cheap and easy to replace rapidly. Or, if you use liquid metal liners, you face all the complexities of handling those we just discussed. Companies like General Fusion are pursuing this liner implosion approach.
Okay. MTF-MIS is one hybrid. What else is out there?
Another fascinating concept, which is actually one of the very earliest ideas for magnetic confinement, but is seeing a modern resurgence, is the Z-pinch.
The Z-pinch. Sounds electric.
It is. In its purest, simplest form, a Z-pinch device doesn't even need external magnetic field coils for confinement.
Yeah.
You simply drive a massive pulse of electrical current, typically millions of amps axially in the Z direction, through a column of plasma maybe formed initially from a gas puff or a frozen fiber.
Just run a huge current through it.
Yes,
This huge axial magnetic current generates a powerful axial magnetic field.
a field that wraps around the plasma column. This magnetic field then interacts with the current itself via the Lorentz force to create an inward pressure that pinches the plasma column, rapidly compressing and heating it.
So the current creates its own confining field. That sounds elegantly simple.
It is appealingly simple and potentially very compact. Z-pinches are known to be very efficient at converting electrical energy into plasma energy, and they can create extremely high density and high temperature plasmas. Large pulsed power machines driving Z-pinches have produced the highest laboratory X-ray powers ever achieved, actually.
So why isn't it the main approach? There must be a catch.
A huge catch. The simple Z-pinch configuration is notoriously violently unstable. It's highly susceptible to fast-growing MHD instabilities, particularly the sausage mode, where the column pinches off in places, and the kink mode, where the column develops helical wiggles. These instabilities typically cause the plasma column to break up in microseconds, long before significant fusion burn can occur. This fundamental instability problem led to the Z-pinch being largely abandoned for fusion energy research for many decades.
So it collapses too quickly. Is anyone trying to fix that?
Yes, that's where the modern resurgence comes in. Several groups and private companies, notably Zap Energy, are pursuing concepts based on stabilizing the Z-pinch. One leading idea is the sheared flow stabilized Z-pinch. The concept here is to introduce a strong axial velocity shear within the plasma column, meaning the outer layers of the plasma flow much faster along the axis than the inner core. Theoretical work and experiments suggest that this sheared flow can potentially suppress the growth of those deadly kink and sausage instabilities.
Flowing the plasma to keep it stable.
That's the hope. If they can demonstrate stable confinement for significantly longer times than the instability growth time, The Z-pinch could reemerge as a potentially simpler, more compact path to fusion. But proving stability at reactor-relevant conditions is still a major hurdle.
Okay, one more. Any other particularly interesting alternatives?
One more that's gained significant traction, particularly in the private fusion sector, is the field reverse configuration, or FRC. You can think of this as the efficient smoke ring of magnetic confinement.
Smoke ring?
It's a unique magnetic confinement topology. An FRC is essentially a self-contained torus, donut shape of plasma, that has closed magnetic field lines. But critically, it achieves this without a central column or any toroidal field coils linking through the center of the torus, unlike a tokamak or stellarator.
How does it hold itself together then?
It's confined primarily by a poloidal magnetic field running the short way around that is generated by strong electrical currents flowing toroidally, the long way around, within the plasma itself. This creates a self-organized structure where the magnetic field lines inside the plasma ring point in the opposite direction to the externally applied magnetic field lines outside the ring, hence the name field reversed configuration. It looks a bit like a smoke ring of plasma carrying its own magnetic field.
Okay, a self-contained magnetic smoke ring. Advantages.
FRCs have several potentially transformative advantages that make them very attractive.
Yeah.
First, they have a naturally very high beta. Beta is the ratio of plasma pressure to the confining magnetic field pressure. FRCs can operate with beta close to 1, meaning the magnetic field is used extremely efficiently to hold the plasma pressure. Tokamaks and stellarators typically operate at betas of only a few percent.
High beta means efficient magnet use.
Which is good. Second, their basic geometry is a simple cylinder, without the complex interlocking coils of toroidal devices. This could make reactor construction, maintenance, and particularly access for things like blanket replacement much simpler and potentially cheaper. Third, this high beta nature and linear geometry make FRCs theoretically well suited for burning advanced aneutronic fusion fuels like deuterium helium-3.
Neutronic meaning fewer neutrons.
Ideally, yes. The DA reaction primarily produces charged particles, protons and alpha particles, rather than high-energy neutrons. If you could burn these fuels, you could potentially reduce neutron activation of the reactor structure dramatically, simplify the blanket design, no need for tritium breeding, and maybe even enable direct conversion of the charged particle energy into electricity at high efficiency. This is a long-term holy grail for fusion.
Wow. Efficient, simple geometry, advanced fuels. FRCs sound amazing. What's the catch this time? There's always a catch.
The perennial catch for FRCs has been achieving stability and good confinement, especially against a particularly nasty global instability called the tilt instability, where the whole smoke ring tries to rapidly flip over and destroy itself. Forming FRCs and sustaining them in a hot, stable state for long enough durations, milliseconds or more, to achieve significant fusion gain has proven extremely challenging, especially as they are scaled up to larger sizes.
So keeping the smoke ring from tilting or dissipating too quickly.
Exactly. However, several private companies, notably TE Technologies and Helion Energy, have made significant progress in recent years. They are pursuing innovative methods for forming, heating, often using powerful neutral beams, and sustaining FRCs, and claim to be overcoming some of these historical stability challenges. They represent another important front in the broader exploration of fusion concepts beyond the mainstream.
Okay, wow. We've covered a lot of ground in these 4 episodes on fusion technology. We've taken a really deep dive into the incredible physics that underpins fusion energy, from that basic DT reaction and the crucial role of alpha particles, right through to the complex interplay of density, temperature, and confinement time captured in the Lawson criterion and the triple product. We've explored the 2 leading contenders in this race: magnetic confinement, with its tokamak workhorse and complex stellarator challenger, and inertial confinement, with its laser-driven mini-explosions and the NIF ignition breakthrough. And we even touched on some of those fascinating frontier explorers like MTF, Z-pinches, and FRC.
Yeah, it's a huge landscape.
And throughout all of this, we've really tried to reinforce those grand challenges that cut across nearly all approaches. The sheer difficulty of controlling that wild, turbulent plasma, the brutal challenge of managing the extreme plasma material interface, the heat, the particles, the neutrons eating metal, and ultimately the bottom line goal of achieving net energy gain in an efficient, reliable, and hopefully economical system.
It really brings up an important question, or maybe just a point to ponder for you listening. It should be clear by now that there's no single best approach to fusion, at least not at this stage. Rather, each concept we've discussed represents a different set of calculated risks and technological bets.
Different paths up the mountain, like you said.
Exactly. The ultimate success of fusion energy might very well depend on which specific set of incredibly difficult engineering complexities proves to be more tractable technologically and economically. Is it ultimately easier to learn how to reliably manage plasma instabilities and disruptions in a tokamak? Or is it easier to master the art of building incredibly precise, intricate coils for a stellarator? Or perhaps the biggest hurdles lie in mastering the mass production of perfect tiny targets and building hyper-efficient drivers for ICF. We just don't know yet which set of problems will yield first.
So the journey continues.
Absolutely. The journey to harness the power of the stars is definitely not a single horse race. It's a broad, complex, and absolutely vital scientific and engineering exploration unfolding across multiple fronts simultaneously.
And while we've really unpacked the incredible science and the daunting engineering behind these fusion machines and their core challenges today, there's an even bigger picture to consider, isn't there?
There certainly is.
So in the final part of this series, we're going to zoom out from the physics and the machines. We'll explore the broader implications of achieving fusion energy, what it could mean for the global energy sector, for climate change, for the economy, and maybe even for society in general. What would a world powered by fusion actually look like?
That should be a fascinating discussion.
I think so too, so you definitely don't want to miss that. Until then, keep exploring, keep questioning, and make sure that you're subscribed to Signal 2030.
Bye for now.